Let's now talk about the idea of calculating sample sizes for proportion. The sample sizes, we're going to make this calculation so that when we go out, we know what size of sample we should take. How many people should we contact for this survey or whatever it is that we're actually doing? How do we know how many to contact? Well, this is what we need to start thinking about and doing. We couldn't do it prior to this, even though we talked many chapters ago about actually going out and taking surveys, taking samples, different sampling techniques. We always just said based on the sample size. Well, we couldn't really specify what the sample size was back then because we didn't have the tools available to us to do it. Now we do. Okay, I want to emphasize once again that confidence intervals are always about population parameters. We use our sample statistics to estimate population parameters. We use our sample statistics to actually construct a confidence interval, which is used to estimate a population parameter. Now, before we go out and take a sample, we must first know what the sample size will be. We need to know what size of sample that we're going to actually obtain. Now, in order to calculate the sample size, we need to know two things. The first is the margin of error, and the second is a level of significance. Remember, that's alpha. So if I have a 2% level of significance, 1 minus 0.02 is 0.98, I'm going to build a 98% confidence interval. The margin of error says, once I have my point estimate, how big is this interval? Margin of error is actually half the width of the interval. So, when you go out and collect the samples, it can be based on the idea of ensuring that your margin of error will be small enough to make your interval useful. You don't want to go out and spend hours and hours and hours and a lot of money to put together a study to go out and collect some data and come back and find out your interval is too big to be useful. It's a waste of time and resources. So we will specify the margin of error ahead of time and then make sure our sample size will get us a margin of error equal to what we specified or less. Okay, now the quantity z of alpha over 2 times the square root of p hat, 1 minus p hat over n, is actually known as the margin of error. This is the ME. Now, the value of z is actually specified by the level of significance. It's specified by alpha. Yeah, right there is the alpha. So once we have that, once we have alpha, we have z. Okay, now to calculate the sample size, all we're going to do is say this is the margin of error. So we're going to set it equal to what we specified the margin of error to be. Maybe 1.5%, 2%, 3%, whatever. And then just solve for n. So when we do that, this is what we get. Let's see, let's just do a little algebra here. I have the margin of error equals z of alpha over 2. I'm going to skip the alpha over 2 just because of the way I'm writing it. Makes it a little bit easier. P hat, 1 minus p hat over n. That would imply that the square root of n equals z times the square root of p hat, 1 minus p hat, divided by the margin of error. That would imply that my sample size is equal to z times the square root of p hat, 1 minus p hat, divided by the margin of error with the whole quantity squared. So there's my sample size. But, obviously, there's a problem. The reason we're doing this is so that we can go out and collect a sample and calculate p hat. Right in the middle of my calculation is p hat. I need to do something about that. So what I'm going to do is, absent any other information, I'm going to use a half, which is 0.50, however we want to write it, for our estimate of p hat. Now, this estimate of p hat is only for sample size calculations. Once we go get our sample, we actually calculate p hat and we'll have it. Why would I use a half? I'm glad you asked. Look at this graph. The reason we use a half as our estimate of p hat is because it's a safe value to use. Now, by safe value, this x-axis, okay, the x-axis here, what the heck? Can you just edit that out? I'm not touching anything. I don't know why it's going. Okay, the x-axis here is actually the p-hat axis. And the y-axis is actually the n-axis, the sample size. Notice when p-hat is at a half, that is the peak here for the maximum value, the biggest value of n, the sample size. So, if I don't know what p-hat is going to be, by using a half as my estimate for p-hat, let me write a better p there. By using a half for my estimate p-hat, I will get a safe sample size. It's also the biggest sample size possible. Now, it may not be, this axis is 2,000, 4,000, 6,000, 8,000. I don't recall what I used for this. I probably used a level of significance of like 0.01, because the level of significance will also make a determination as to what the y-axis is. So these numbers here are really not as important as is the shape of this graph. This graph is sample size as a function of the sample proportion. If in reality I go out and calculate go out and get my sample and I end up with something like down here, what that means is I really didn't need as big of a sample. I could have gotten away with something way down here rather than having a sample size up here. I could have saved myself. Well, all that's going to mean is that I have more samples than what I really need, so that my margin of error will end up being smaller than what I specified. If I specified 1.5% from a margin of error and calculate it using 0.5 as my estimate for p-hat, and I actually end up with like 0.22 or 0.21, well, I had more samples than I needed, so the standard deviation is going to be smaller, and I will get a smaller confidence interval. And that's good. A smaller confidence interval is good. Okay, so actually, let's go back to this for a second. So my sample size calculation will now look like n equals z of alpha over 2. We'll specify that value z depending on alpha, times the square root of 0.5 times 1 minus 0.5 divided by whatever we specify as our margin of error squared. And obviously, there's some algebraic simplification that you can do here if you want, and I'll let you figure that out if you want to. Either way, this will work either way. Okay, let's go ahead and calculate some sample sizes now. I want to calculate the needed sample size for a proportion given the following criteria. Now, all these are based on a level of significance of 0.05, 0.05, 0.05. So, level of significance is staying the same. The margin of error is 0.05, and then we'll calculate again using a smaller margin of error, 0.03, and then a smaller margin of error, 0.01. Now, if the level of significance is 0.05, the size of the confidence interval is going to be 0.95, because 0.95 plus 0.05 is 1. All these are 95% confidence intervals. So, what will the sample size be? Well, I'm not going to do these by hand. Let's go to the calculator and take a look here. If you go to Program, PRGM, it's in the middle toward the top of your keypad. And go to the program called SAMP size. There it is. SAMPLE, sample size. There's not enough letters here in the calculator to allow me to make it say sample size. That's the best I could do. Now, if you don't have that program, contact your instructor. They're made available for your instructors, but obviously it's each instructor's own decision whether they actually want to use it or not, or perhaps they want you to calculate by hand. That's a personal decision. But if I run sample size, set select, and then it says PRGM sample size, it's ready to run. Hit enter again. Now, am I calculating a sample size about an inference regarding the mean or a proportion? In this case, it's a proportion, so I'm going to select option 2. What's the margin of error? Well, it said margin of error for our first one was 0.05, so 0.05. What's the confidence level? Well, that's the size of the confidence interval, right? The confidence level, not the significance level, it's the confidence level. Significance level is 0.05. The confidence level is 0.95. Hit enter. It says believe proportion. If you have evidence that the proportion would be close to like 0.1, 0.15 right in there, then you could use that prior information. Absent that prior information, we'll use a half. Hit enter. And it says my calculated count sample size is 384.14. All right, so let's go back and take a look. 384.14, that means I'm actually going to get a sample size of 385. I can't get 0.14 over person, so if I have anything other than all zeros to the right of the decimal, I'm going to round up. I'm going to go up and go to 385. Okay, now what happens when I do the same calculation, but this time the margin of error is going to be 0.03. All right, let's go back to the calculator. If I just hit enter, it's going to run that program again, because that's the last thing I did. Select proportion. The margin of error is now 0.03. Everything else will be the same. It's a 95% confidence interval, and I'm using 0.5 as my belief initial proportion. Now I need 1,067.072. All right, let's go back and write that down. I need 1,068. Remember, I'm going to round up. The last one says my margin of error is 0.01. All right, let's go back to the calculator. Hit enter. I'm doing a proportion. Margin of error is 0.01. I'm still doing 95% confidence interval. My belief proportion is still 0.5. Now I need 9,603.64. So actually what I'm going to record is 9,604. Whoa, look what happened to these sample sizes. If I can do a margin of error of 5%, that's my point estimate, plus or minus 5%, I only need a sample of 385 to be safe. It's possible it could be less. It depends on what the sample proportion actually comes in at. If I just decrease that margin of error by 2%, going from 5% to 3%, I jump from 385 to 1,068. That's over double. That's over double. If I drop it yet another 2% and say I want to be within 1%, I want to be very, very, very accurate with 5% chance that I'm missing, that means 95% probability that the proportion is actually in there. Man, I just went to 9,604. That's huge. Well, what this is saying is that as I decrease my margin of error, particularly with the proportion, this is amplified with proportions. If I decrease the margin of error, I've got to make my sample size bigger and bigger and bigger. Well, think about it. The margin of error was z of alpha over 2 times the square root of p hat times 1 minus p hat divided by n. Well, if I'm making my margin of error smaller and smaller and smaller, z doesn't change. That's been the same. P hat, I'm going to say, is the same. In terms of these calculations, one thinks that p hat is going to be the same. To make the margin of error smaller, the only way I can make this whole thing smaller is make n bigger and bigger and bigger. As n gets bigger, this ratio gets smaller. As this ratio gets smaller, the square root of the ratio gets smaller. Square root of the ratio times z of alpha over 2 gets smaller, so the margin of error gets smaller. Because we're taking the square root, the size of n just gets huge, as you can see down here. Okay, I'm going to do the same thing now, only this time I'm going to keep my margin of error at 0.05. And all I'm going to do is change my significance level. Well, the size of the confidence interval, if my significance level is 0.05, is 0.95. If it's 0.02, then the size of the confidence interval is 0.98. If it's 0.01, it's 0.99. In this last example, let's go back there. These are all 95% confidence intervals. Significance level stays the same, but the margin of error got smaller. Now, I'm keeping the margin of error fixed at 5%, and I'm changing the confidence level. So I'm more and more and more certain that the true proportion is going to be in my interval. 95% certain, 98% certain, and then last but not least, 99% certain. Okay, let's go back to the calculator and see what we get. I'm going to hit enter again to simply rerun that program. I'm talking about proportion. Okay, margin of error is 0.05. Confidence level is 0.05. Oops, I'm sorry, 0.95. And the belief proportion is 0.5. That's 384.146. That's 385. Yeah, that's the exact same one we calculated a few minutes ago. Everything here was the same. Now, we're going to change that significance level. Let's go back to the calculator. To the proportion. The margin of error is now 0.05. It didn't change. The confidence level did change. I went from 0.95 up to 0.98. So I'm more certain that the parameter is going to be actually in there. And my belief proportion is still 0.5. Now I went to 541.18. So what would I record? I would actually record 542. This is the sample size I would need to get. Now let's jump to 99% confident. Again, in proportion, margin of error is still 0.05. My confidence level is extremely high, 99%. Belief proportion is a half, 663.49. So what will I record? 664. Okay, what changed here? Well, if I change the significance level, really all I'm doing is I'm changing this part. I have z of alpha over 2 times the square root p hat 1 minus p hat divided by n. This is what I'm changing. By changing the level of significance, I'm changing alpha. The level of significance is alpha. The size of the confidence interval is 1 minus alpha. So all I'm doing is I'm changing the z value. And you can see that the effect on the sample size is not nearly as dramatic as it was changing the margin of error. All right, let's go ahead and do one for real now. I want to calculate the recorded sample size if a survey will be used to estimate the proportion of persons in favor of a particular measure on some upcoming election. Now, I need to be accurate within 2.5% with 98% certainty. Okay, this has told me that my margin of error equals 0.025. 98% certainty. This is saying that the confidence level, let's say C level, equals 0.98. That implies that alpha, the significance level, is 0.02. So go to my calculator. Again, in proportion. See, margin of error is 0.025, 2.5%. Confidence level is 0.98. And the belief proportion, I don't know anything. I don't have any prior knowledge, so I'm going to stay with 0.5. This is saying I need 2,164.75. So I will come back and record that n, my sample size, must be 2,165. That's how big of a sample that I need to get to ensure, to be certain that when I actually go ahead and calculate my sample proportion and I build that confidence interval, that the margin of error will be no bigger than 0.025. If, in fact, my sample proportion turns out to be 0.5, my margin of error will be exactly 0.025. If it's anything other than 0.5, go back to this slide. If it's smaller there, if it's bigger, like up here someplace, that's the sample size I needed. So if it departs from 0.05, anything other than that, then my confidence interval will actually be smaller, which is a good thing. If I want to have a level of significance, or I'm sorry, margin of error of 2%, but I end up with a margin of error of 1%, well, that's a good thing. If I want a margin of error no more than 2%, but I end up with 3%, that's a bad thing. The margin of error is too big. It's much bigger than what I wanted. Okay, that's going to wrap it up for proportions. I believe our next step will be take a look at the same concept, only applied to the mean.